Alright, today we're going to be talking about mineral groups. We're going to talk about the first 3 mineral groups. Tomorrow we'll talk about the other 3 mineral groups. But as I mentioned in the intro to the week, there actually are over 3,800 minerals that have been named. Probably more than that since the textbook I got that information out of was published. But yeah, probably more than that because we keep identifying new ones every year. And even though there's 3,800 of them, we're not going to try to remember all 3,800. We're going to stick with some of the most common minerals. And we talked about some of the most common elements that we find in Earth's crust. And those were oxygen, that was number 1. It was about 47% of Earth's crust is made out of oxygen, or has oxygen in it. Second was silicon, and then we get into aluminum and iron and calcium, and then it goes on down. Sodium, potassium, magnesium, and then a bunch of others that take up a very, very small, like less than 2% of the makeup of Earth's crust, or other things other than what I just mentioned. So there are these groups that we categorize minerals into, and the first one we're going to talk about is silicates. That's S-I-L-I-C-A-T-E-S. It's in the corner. So we talked, like I said, about those elements that are common, and we said that oxygen and silicon were the 2 most common elements in Earth's crust. Well, they actually combine to form a structure that we call the silicon-oxygen tetrahedron. It's one of those big vocab words. And so a tetrahedron, if we break that down, the tetra means 5, right? So the tetrahedron means it's 5-sided. So this structure is shown in an image in the reading. If you check the reading out, or here in the video, we have an atomic model image of it, so you can see how the atoms are kind of bonded together, and they form almost that triangular shape that creates the top of the crystal that forms in a silicon-oxygen tetrahedron. And there's basically 4 oxygen atoms and 1 silicon atom that provide the framework for each silicate mineral. And then you get a bunch of these compacted together, and you get these beautiful crystals that we're familiar with, that we might know as quartz. So most silicate minerals, except for a few, like pure quartz, contain some other elements as well. But pure quartz is simply just silicon and oxygen. That's it. So the tetrahedron can actually join in a bunch of different ways up with other tetrahedrons. And quartz crystals obviously shows that. There's literally millions of molecules of that mineral creating those long crystallized structures, and they're very beautiful. And these bonds that hold them together between the silicon and the oxygens are actually very strong. Some minerals, we've got things like olivine, they simply have millions of these single tetrahedrons, and that's all they're made up of. We also get the tetrahedrons to form in long chains in things like augite. And then we get these double chains that kind of run side by side or parallel to one another, and they form in sheets. We know this as hornblende. And then we obviously are going to find this 3-dimensional network of structures in other silicates like quartz, which we mentioned, and things like feldspar. You can look that up if you want to see what that looks like. And we're going to find out that the internal structure of minerals affects its properties as we move on through these lessons. So now it's time for you to pause for a moment, pause the video, and answer the following question. What is the silicon-oxygen tetrahedron, and in how many ways can it combine? Now keep in mind, before you pause the video, that down below you can actually see some content, some embedded content that covers this same information. It reinforces what we're talking about here in this video. So check that out. It'll help you to answer the question. This is going to be part of what you turn in today. So go ahead and pause now, and then come back when you're done. All right, welcome back. So we want to remember that we talked about silicate minerals crystallizing from magma back when we were talking about the rock cycle. This happens as it cools, and this cooling can occur either right at Earth's surface or just below, where the temperatures and pressures are reduced, or greatly reduced from what they were deeper down into the towards the core. So the formation of silicates can also take place not just near the surface, but they can also take place very deep where the temperatures are high and the pressures are high as well. So they can really form pretty much anywhere, but where they form and the chemical composition that they have, and the chemical composition of the magma, of course, that's where they're coming from, is going to determine which silicate minerals will form. Just to give you an example, silicate olivine crystallizes at temperatures of about 12,000 degrees Celsius. That's really, really hot. But quartz, something you're more familiar with probably, that crystallizes at only about 700 degrees Celsius. Still really, really hot, but nothing like the 1200 degrees Celsius that we find a little deeper. We've even got some silicate minerals that'll form right up at the Earth's surface whenever these minerals get exposed to weathering. And weathering could be wind, rain, you name it. It could be all of those things. Clay minerals, which are silicates, this is how they form. And then we've even got other silicate materials that come from under extreme pressures that occur when mountains are being formed. So we've got silicate minerals that can often provide scientists with all kinds of clues about the conditions in which those minerals were formed. Because of the conditions helping to basically specify what minerals can form, that kind of gives scientists a clue. When they find the minerals, they can kind of reverse that and go, oh, well, if that's the mineral I have, then these must be the conditions, because those are the conditions required when these minerals form. So they can kind of go either direction on that. So that brings us to our second group, and the second group are our carbonates. And so carbonates are about the second most common mineral group, and they're basically minerals that contain the elements carbon and oxygen and one or more other metallic elements. Calcite is a good example of this. In fact, it's one of the most common carbonate minerals. Well, that's like a tongue twister. Common carbonate minerals. There we go. And dolomite, I don't know if you've ever heard of dolomite. It's another carbonate material that contains magnesium and calcium. And both limestone and marble, limestone we find a lot here in Pennsylvania. If you go down to rivers and things like that, you'll find a lot of limestone. And marble we use for construction. We use that for like countertops and things like that. Those are rocks that are composed of a lot of carbonate minerals. All right. So our third and final group for minerals is the oxides. And oxides are simply minerals that contain an oxygen and one or more of the other elements. And those other elements generally tend to be metals. And some oxides, including a mineral that we call rutile, is one that forms as the magma is cooling deep, deep, deep below Earth's surface. And rutile is basically the more, I guess, scientific name would be titanium oxide. So it's TiO2. So there's 2 oxygen for every 1 titanium atom. We've got other oxides. We have things like corundum, and this is basically formed when minerals are subjected to changes in temperature and pressure, which we talked about before. And it's basically aluminum oxide. So we get aluminum from that mineral, and we get titanium from the titanium oxide. So there's kind of a clue there. Titanium oxide we get titanium from, aluminum oxide we get aluminum from. See where I'm going there? So other oxides, things like hematite, I like that one, it's almost like my last name. That's Fe2O3, so It forms when existing minerals get exposed to liquid water or to just moisture in the air. And hematite is one form of iron oxide. So that brings us to our second question, our second you do, and that is, what do you think we mine for when we're mining iron oxide or hematite? What is the element we're mining when we are mining hematite? Okay, so that's the end of today's lesson. Answer that question and the previous you do question and submit those as today's assignment. Thank you very much. Have a great day.